CHEM 1 lab, vapor pressure of pure liquid. When two phases, alpha and beta, are in equilibrium at a certain temperature and pressure, the Gibbs energy of the system must remain constant even if there's an exchange between the two phases. And this leads to the criteria for phase equilibrium, and that is the chemical potential must be the same. When temperature pressure changes, in order for the two phases remains in equilibrium, the change of pressure temperature must meet the Clapeyron equation, and that is dP over dt equals delta S over delta V. Delta S is the phase transition entropy. Delta V is the phase transition volume change. Because delta S for phase transition is calculated by delta H over T, so Clapeyron equation can be also written as dP over dt equals delta H over T delta V. Clapeyron equation applies to all phase transitions. When Clapeyron equation is applied to liquid-vapor phase transition, several assumptions can be made. One is delta V is the volume change for the phase transition. In this case, is from liquid to gas phase. Now, because liquid volume is much smaller than gas volume, so delta V can be approximated to be volume of the gas. If gas phase obeys ideal gas law, then this volume can be calculated by RT over P. If we assume the vaporization enthalpy is a constant, then the Clapeyron equation can be integrated to be Class's Clapeyron equation. In this equation, ln P2, so here P2 is the vapor pressure at the temperature T2. P1 is the vapor pressure at the temperature T1. Alternatively, this equation can be written as ln P equals negative delta H over R 1 over T plus A. So ln P1 and 1 over T1 combine together as A, and P2 is the pressure change, vapor pressure, and T2 is the temperature. So this equation tells us how the vapor pressure change as a function of temperature. Now compare with y over kx plus b. So ln P is y and 1 over t is x. So this equation suggests that ln P and 1 over t is linear. If we plot ln P against 1 over t, we should get a straight line, and the slope k is negative delta H over R. So if we measure the vapor pressure at a different temperature and plot ln P over 1 over t, we get a straight line, and from slope we can find the vaporization enthalpy. In deriving this Class's Clapeyron equation, we made some assumptions. One is the gas is ideal gas, and the enthalpy of vaporization is constant. In reality, the vaporization enthalpy may not be constant. It's temperature dependent, and the gas may not be ideal. So to calculate volume, the gas law should include compression factor Z. And the derived Class's Clapeyron equation also include a Z factor. So if we plot ln P versus 1 over t, the slope should be negative delta H over Z times R. So in order to calculate delta H using this slope, we must know the Z factor. In our handout, there's a graph showing Z factor as a function of reduced temperature for several liquids. And this graph shows that when temperatures increased, the Z factor decreased. And that suggests that the slope actually is not constant, because delta H divided by Z, and when you increase temperature, Z decreases, and so the slope should increase. Okay, so that means that if we plot ln p over 1 over t, you shouldn't get a straight line, okay, because slope changes with temperature. It turns out that our experiments show this curve, ln p versus 1 over t, is actually quite a straight line. And this is because even though z decreases with temperature, delta H also decreases with temperature. Delta H is temperature dependent, that's described by Kirchhoff's law. And this says that the enthalpy of vaporization at T2 should be the enthalpy of vaporization at T1 plus integration of the delta Cp over temperature. Delta Cp is the heat capacity difference between liquid and the gas phase. Now, if this delta Cp is a constant, then this equation can be simplified as delta H at T2 equals delta H at T1 plus delta Cp times delta T. Again, this delta Cp is the heat capacity difference between the liquid and the gas phase. Again, in our handout, there's a table shows delta Cp for different liquid. For example, for benzene, delta Cp is negative 54. A negative number here indicates that when you increase temperature, delta T is positive, the enthalpy of vaporization decreases. Okay, so therefore, because Z decreases with temperature, delta H also decreases with temperature, so the slope is actually quite close to a constant. And therefore, the plot of ln p over 1 over t is reasonably a straight line. Okay. Now, using this plot, and we get delta H over ZR should be considered an average value, okay, in the measured range. For example, if we measure vapor pressure at temperature 25 to let's say 75 degree, okay, in this range, so the measured slope delta H over ZR should be average value in this range, okay, and therefore we can find the midpoint. Okay, so in this case, midpoint is 50 degree. Okay, so convert 50 degree to Kelvin, and then in this graph, all right, so we can find the reduced temperature. For example, benzene, the critical temperature is 563. So using the midpoint temperature, we can calculate the reduced temperature somewhere here, and we find the Z factor. Okay, and using this Z factor and the slope, we calculate delta H, the vaporization enthalpy. But remember, this is the midpoint vaporization enthalpy. In this case, okay, in this example, it should be 50 Celsius delta H. Now, how do you calculate delta H at boiling point or at 25 degree? Okay, we use this Kirchhoff's equation, and this is 25 or this is 50 degree. In order to calculate 25, okay, so here is 25, so you use delta Cp here is negative 54, and then delta T is T2 minus T1. Okay, so because T2 in this case is smaller than T1, and so it's a negative number, and delta Cp is also negative, you add a positive number, and that gives you a larger number. So low temperature gives you a larger delta H. On the other hand, when you want to calculate delta H for boiling point, in this case for benzene, it's 80. So this is 80.1, okay, for benzene. So here 80.1 minus 50, and that gives you a positive number, but delta Cp is negative, and therefore the calculated delta H at 80.1 should be smaller than the value of 50. Okay, so you calculate the enthalpy of vaporization at room temperature or 25 degrees should be greater than the value at 80.1, the normal boiling point vaporization enthalpy. In this experiment, a glass thermostat vessel is used to keep a temperature constant. The vessel includes a large water bath, a heater, a stereo, and a thermometer. The key of this experiment is the isoteniscope. The liquid we want to measure is placed inside a small glass bulb of this isoteniscope. The same liquid fills part of the U-tube of the isoteniscope. After the system is evacuated, the pressure above these two liquids inside the isoteniscope is only due to the vapor phase of the liquid. In other words, here is the vapor pressure of the liquid that we want to measure. If we can adjust the level of the liquid of the U-tube so that the two sides has same level, then the pressure of the left side equal to the pressure of the right side. The pressure of the left side is the vapor pressure of the liquid, and the pressure of the right side can be measured by a manometer. The isoteniscope is connected to the manometer through a ballast bulb. At the bottom of the ballast bulb, there is a three-way stopcock, and this is used to control the levels of the liquids inside the U-tube. For example, suppose inside the U-tube, the liquid on the left side is higher than the right side. That indicates the vapor pressure at the left side is smaller than the pressure on the right side. So the right side push liquid to the left side. In other words, the pressure is too high on the right side. In order to measure the vapor pressure, we need to reduce the pressure on the right side. To do that, we rotate the three-way stopcock so that the system is connected to the pump. Okay? After evacuate some air, the pressure is reduced. Liquid move to the right side. Eventually, left side, right side becomes equal height. At this point, the reading of the manometer is the vapor pressure of the liquid. On the other hand, if inside the U-tube the right side is higher, that means the vapor pressure at the left side is higher than the pressure on the right side. So it pushes liquid to the right side. So the pressure on the right side is too low. In order to measure the vapor pressure on the left side, we have to increase the pressure of the right side. To do that, we rotate the three-way stopcock to let air inside. So we rotate to connect to the air. So let some air inside the system to increase the pressure, push liquid to the left side. Eventually, the two levels of the liquid again becomes the same. At this point, the reading of the manometer equals the vapor pressure of the liquid. Before placing the sample in an isoteniscope, evacuate the system and check for leaks. And then add the liquid to 2/3 of the bulb. Place the isoteniscope in the thermostat and connect it to the ballast bulb. Pump to sweep air out of the bulb for 4 minutes. And tilt the isoteniscope to transfer some liquid to the U-tube. Adjust the three-way stopcock to maintain the level of the liquid equal at the two sides of the U-tube. Read and record the temperature, the mercury height in manometer. Remember, manometer measures the pressure difference between the system and the atmosphere. So you also need to read the barometer. Using barometer minus manometer, that gives you the pressure of the system. You need to make sure all the air is removed from isotoniscope by repeating the procedure above until successive readings are in good agreement. And then you can heat the thermostat bath to a different temperature and keep the liquid levels in YouTube equal. Record the different temperature and the corresponding reading of the manometer. For benzene, here are some suggested temperatures. We start at 25 degrees and increase temperature 5 degrees to 30 and then 35 until 75. And then cool down the system to the temperature between these numbers. For example, 72.5, 67.5 until 27.5. And remember to record the manometer readings. In your lab report, you should list all the results in one table. This includes a column of temperature in Celsius, temperature in Kelvin, and then one column of inverse temperature. And then the readings of the manometer, so mercury height H1, H2, and using this to calculate the pressure. Okay, the reading of manometer should be the difference between these two mercury height, so H2 minus H1. Okay, so that's the reading for manometer, and the pressure is calculated by barometer reading minus manometer reading. And finally, one column of natural log of the pressure. Now give a graph of pressure versus temperature. Okay, note that this graph shouldn't be a straight line because pressure temperature is not linear, but this graph will give you a good indication whether the two different data sets are in good agreement. One data set is due to the temperature increase, okay, heating. One is for cooling. If they are in a good agreement, they should interspaced and fit in one curve. And you should also see the vapor pressure increase significantly with temperature. And now plot natural log pressure against inverse temperature. If the experiment is done correctly, and this should give you a reasonably straight line. Okay, and from this straight line, you can calculate the slope, okay, which is delta H over RZ. You can do this by Microsoft Excel linear fit. Okay. Now remember, this is for the average temperature in the temperature range of the measurements. So you need to find the average temperature, calculate the reduced temperature, and then use this reduced temperature to find the Z factor. Okay, plug in this equation, the slope, you calculate the vaporization enthalpy. Okay, this vaporization enthalpy is at the average temperature. So using this data, you calculate the vaporization enthalpy at the normal boiling point and at 25 degree or 298 Kelvin. So for benzene, normal boiling point is 80.1. Okay, this calculation can be made by using the data CP given in the handout. Compare your results with literature values. If they are not in good agreement, you should discuss in your lab report what reason do you think it is, and how do you improve the experiment, and calculate the entropy change at the normal boiling point. Equation is delta H over T, and compare with the Charton's rule.